Sure. So, good morning, everyone. I'm presenting a paper called Deep Goal Reasoning and Analysis. This is work with Weihang Yuan, who is a PhD student at Lehigh University. I'm Hector Munoz-Avila. This work is funded by the National Science Foundation and the Office of Naval Research. A disclaimer, any opinion, findings, and conclusions or recommendations in this presentation are those of the author and not necessarily those of the National Science Foundation. So let me start by the Goal Act architecture. So the Goal Act architecture is a planning, execution, and learning system. It has two layers, the goal selector and the actor is directly interacting with the environment. The first thing I should say is that this goal architecture is a direct extension of a system called HDQN developed by Josh Tenenbaum and students. So we just added a few more inputs that are needed because some extensions of HDQN developed by other authors use those inputs. So we wanted to analyze it, and that's why we added these additional inputs, and we renamed the layers to give it more declarative meaning, but it's basically HDQN. So let's start with the top layer, the goal selector. The goal selector receives as input the state S and additional inputs I, and I will explain later what those additional inputs could be. Based on those inputs, it will select a goal. And at that point, the goal selector gives control to the actor. The actor receives as input the state, the goal selected by the goal selector, and an additional input I prime. And based on that, it executes or selects an action which is executed in the environment. And it will continue executing the actions until eventually the actor sees back control to the goal selector, and the goal selector selects a new goal and starts the process anew. So the actor again chooses takes actions based on the goal, the state, and the input I prime. I already said that. So the first question that we wanted to address in this work is, how is the goal architecture situated relative to the goal reasoning paradigm? And that's because this deep reinforcement learning and our community that is looking at goal reasoning are basically, for the most part, disjoint. So we wanted to see if we can bridge the two. So let's start with goal reasoning. This is a rendering of the OODA model by David Aha. This OODA model was originally developed in the 1960s by John Boyd, who was a US Air Force pilot. And he developed this model indicating how pilots should engage in situations. And since then, this model has been used in many different domains. And here this rendering is from David, where David is saying, well, the decide step, for example, what you do there is formulate a goal, and the system will act based on that goal. So a brief view of goal reasoning with this OODA model. So now let's put these two systems side by side, the goal architecture on the left and the goal reasoning on the right, and let's see how they map, or where they map and where they don't. And some of these mappings have some caveat. So the observed state in the OOD model refers to raw sensor readings from the environment. And in the goal architecture, this is represented as a state, which is partially observed. The state can be, for example, a snapshot of an image of what the agent sees, or a simple vector representing a map annotated with the current location of the agent. For some of the domains we did experiments with, we did both. So we have tried both of these kinds of inputs. So it is a good mapping to the observe step in the model of goal reasoning. Then there is the orient step that happened in the OD model. This orient step focuses the agent's attentions. An example in an instance of goal reasoning called goal-driven autonomy, one will generate an expectation X of the outcomes of the actions, and these expectations are then matched against the observed state, and this determines whether the goals are changed or not. In this architecture, there is really no such explicit oriented step. The next one is the decide. The decide step selects the goal to be selected. In this goal architecture, there is only one goal that is pursued at any point of time. And this is important to note, because in goal reasoning in general, we are managing multiple goals. And here is one in more than one goal could be executed in some systems. Here, only one goal is being pursued. The other important note about this architecture is that the list of all possible goals remain fixed. So I'm not showing the internals of the architecture, but this is a deep learning system. The output is basically a vector where every entry is one goal. And if we were to add new goals, we will have to retrain the system, which can take significant amount of time. Finally, the act step. Once a goal is decided, the control is given to the actor, which takes actions. The effects of each action causes the environment to transition from one state to the next. In the current implementation, the actor continues to take actions until the goal is achieved or a fixed number of steps are taken. Now, Van Riemsig and colleagues developed this taxonomy of goals, and we wanted to again map relative to the architecture. The question of declarative, this is different from what John was defining in cognitive architectures. In this taxonomy, declarative means that there is a way to state whether, to determine whether a particular goal is achieved in a state. And these architectures do that. And they also have procedural. Here, procedural means that the goal is basically to execute an action. And that also have that. Concrete versus abstract goals. In the current implementations, the goals are concrete. But I don't see any limitation, so they could be abstract. I didn't check mark just because there is no current implementation of this architecture that does that. Static time versus durative. All of the goals currently are static time, and I don't know even how to do durative goals, so that would require some research. That's why I put a red mark there. Finally, in the current implementation, all of the goals are regular goals. There are no knowledge goals. Knowledge goals, an example would be something like a goal where you need to do information gathering. I don't know of any implementation of this goal architecture that does that. However, I don't see any limitation why they will not be able to do it. Same with goals can be interrupted or not. Interrupted, a goal means the system is pursuing a goal and it finds something in the environment and it interrupts the goal to try another goal. None of the implementation of the architecture does that currently, but I don't see any reason why I would not be able to do that as well. Now I move gears to the second question that we wanted to address about this, is the question of what kinds of outputs is the goal architecture capable of generating. The first question is, what do we mean by outputs? So if somebody is observing this goal architecture and is interacting with the environment, one will notice the states that are visited by the agent that is implementing this architecture. So in this case, we start with the starting state as 0, then we go to a state as 1, etc. So the question is, what kinds of state sequences will we be able to generate when we execute, when we perform, an agent is performing this architecture. So to do that analysis, we went back and looked at Mike Cox and collaborators, what they call the goal formulation rule, that says that beta, that's the name of the function, the next goal G prime is selected as a function of the current state S and the current goal G. So beta of S, G, S comma G produces G prime. So we look at this and then look at HDQN, and we notice in HDQN the next goal is selected as a function of the current state. So it's a variant of this beta rule where given S and nothing else, you will select the next goal. There is another system based on this architecture called funds. Funds there is for feudal networks, and that system uses a history of all of the states previously visited by the agent. So in that case, that function, that goal reasoning rule will say, based on the current state and the list of previously visited state S tilde, we will select the next goal. So then we based on this observation, we generalize Mike-Cox rules to say, okay, so we have this function beta, which receives as input the state and some additional input I, which could be the goal, or it could be nothing, or it could be the history of states, and it would generate the goal based on that. So we start with this generalized rule, selecting the goal G based on S and additional input. Incidentally, when we present the architecture, that's the beta function that is referred to in the goal selector, because this is exactly what it's doing. So what we're going to do is we take this goal reasoning and we want to construct a grammar rule that would capture this, and this is the one we came out with, and I'm going to explain it. So it's a production rule, as it's called. There is the left side, the arrow, and the right side. And I'm going to show you how it captures this beta rule here. So the state is here. So this is the current state, and we just keep it. The additional input is again here, and we keep it. And the goal is added to the right side of the rule. Again, this is basically saying on this input and this state, we are selecting this goal and we add it. These two funny looking things are variables in this grammar. This variable goal represents the goal selector, and this variable act represents the actor. So one way to read this rule is we receive this input I and this state S, and the control, right now the goal selector has the control. After triggering this rule, we will pursue this goal G, and we give control to the actor. So it's basically, this rule is making this transition here. So we look at different instances. For example, in HDQN, then the rule will look like this, because HDQN has no additional input, so it would just be morphed directly like this. In the system like funds, where it keeps this additional input, this history of states, then it would transition like this, and it's a direct instance of this rule. So now we want to build a formal system around these production rules, and we're going to simplify with HDQN. Let me talk about this domain that we use to illustrate it, and this is actually from some of these systems we didn't create it. The basic idea is I have an agent that starts in this location 3. There are two variants. The first variant here illustrated with A is called one visit, where the system will get the maximum reward, the agent will get the maximum reward if it visits this location 6 and goes back to location 0 once. And the two visit variant labeled here B is one where it will visit this location twice and then ends. So we can create a formal system, a grammar modeling this. These two rules here are direct instances of these rules. So if we are in state 3, the next goal to be generated is to go to this location 6. Goal 6 is go to location 6. And the other rule says if you're in location 6, the next goal to be generated is to go to location 0, because it's this goal 0. So these two rules are directly implementation of this. The first rule in the grammar is very simple. We construct one of these for each starting state. So this big S is what in grammar is called the starting variable. The system always starts with starting variable. And S3 is a starting state. So we have this rule that says basically go to the starting state and give control to the goal selector, which is exactly what happened in the goal architecture. If there were more than one starting state, then we'll have more than one of these rules. Then this is a situation where the actor is executing, and it reaches a state where the current goal is achieved, in which case we give control to the goal selector, and that's what this rule is saying. This other rule is saying if we reach a terminal, the actor is executing, is pursuing this goal, and we reach a terminal state, then terminate. Notice that no variable is added to the right side because the system terminates execution. And this rule is for the case that there is an infinite loop. The goal is the actor is executing, trying to perceive this goal, and it never reaches an ending state, and therefore it stays in this infinite loop. So we can show that with this grammar, we are able to solve this problem, or HDQN is able to solve this problem, which maps what HDQN actually does. So we start with this starting variable, we execute the first rule, now we are in state S3. From here, the agent will generate the goal 6, which is going to go to the end. This is executed by the actor, which now means that we are in this state. And again, this based on this state will generate this rule that to go to goal 0. And once this is executed, then it reaches the beginning, the terminal state. So we can construct a grammar that is able to solve this one visit problem. So we have a check mark here because it's able to solve it. We did further analysis, and now we ask what happened with the variant where you visit twice the rightmost location, and basically we are able to prove that it's impossible to generate such a grammar. That of this form is impossible, which mimics what happened with HDQN. It's not able to solve these two visit problem. So then we did the same for the font system, but now it has this memory of states. The instances are here. When it visits S3, then it goes to G6. When it visits S3 and X6, so it has a memory of what it has done before, and this is what is added here. These other rules are exactly the same as with the other system, so the only changes are in the actual goal formulation. Otherwise, it's the same, and that actually mimics our implementation. And basically what will happen is this mnemonic goal act, the one that really uses this memory, is able to solve, we're able to construct grammars, one that solve this problem with one visit, and another one that solves the problem with the 2 visit. So the main results is that we provide a characterization of grammars. The data text sequence, we call it k-mnemonic grammars, and this is case for the amount of memory you have for remembering the states. Using this characterization, we're able to prove that the mnemonic goal act, like for example fonts, is strictly more expressive than basic goal act. And still more expressive here is able to generate the state sequences that are impossible. You cannot construct a grammar that will do that for the basic goal act, meaning HDQN would not be able to solve those problems, whereas fonts can. And we did an empirical evaluation corroborating that, and we did 3 domains: corridor, which is the one I mentioned with the 2 variants. This in this one, the agent received a vector representation of this map. The second one is Doom. In Doom is computer game, but the system is watching a snapshot. He's navigating the same corridor, but the system is receiving this input, which is the actual snapshot of what the agent sees. And when he's moving, it will see it, it will receive a different screenshot. The third one is the grid domain, where we have a task of, we are starting in a location in the middle. To get the maximum reward, the agent has to go to location 0, then go to location 1 and go back to location 0, then go to location 2 and go back to location 0, then go to location 3, go back to location 0, and then go to the terminal state, at which point it will get the maximum reward only when it has done these visits that I indicated.
Hector, it's 5 minutes. I'm sorry, 5 minutes, please.
Thank you. I'll thank you for that. So we did our implementation. By the way, the system is available in GitHub. Weihang put it, and there is a link in the paper, so you can try things yourself. So, but basically, the mnemonic. So the x-axis for this one is the number of training examples, and the y-axis is the performance according to the reward function that I indicated. And in the 3 instances, the mnemonic GOLAC is able to basically learn after a certain number of episodes to solve the problem, whereas the basic GOLAC, which is the one in HDQN, is not able to do to learn to how to solve this problem, which matches our theoretical findings. So there are a number of inspirations for related work. DQN was a system that probably the first system, if not the earliest, probably the first system that combines reinforcement learning and deep learning. So these architectures are all based on this approach. We change on what kind of underlying system we use. In our implementation, we use reinforce, where they use DQN, but it's the basic, the high-level architecture is the same. It's combining reinforcement learning and deep learning. There is a system called DRQN, which uses recurrent neural networks, RNNs, and DQN. They combine both. And we mentioned that here because in our implementation, we are also using recursive neural networks to remember the states that have been visited before. So that's used here. There has a mechanism called options. The idea of an option is I'm executing a policy and I reach a particular state. At that point, I'm going to give a control to a different policy. So option is a mechanism that allows you to jump between policies. So control at some point of time, policy 1 is controlling the agent, but then it's going to a particular state, and then it jumps to another policy, and from that point on, a second policy will be controlling the agent. This is mimicking this GOLAC architecture is doing that because we are changing goals, and we are changing goals, then we are changing the kinds of actions that will be generated. Only all is encoded into the network. The next one is, thank you for the anonymous reviewers. They suggested that we look at memory-based reinforcement learning. We look at those, and indeed it's related to this work. Memory-based reinforcement learning will consider rewards based on the state visited, which is exactly what mnemonic GOLAC is doing. And finally, this work is also related to sub-goal learning, where you have a collection of goals and you decide which goal to choose. That's exactly what the goal selector level is doing. Is learning which goal to choose based on maximizing the reward. And this is my last slide. It's a conclusion, a collage from things. The first is we did a mapping between the OOD and the GOLAC architecture, and we saw some things that map, others that don't map, and there are some caveats in when they map. So, for example, the big caveat of the in goal reasoning, when we are managing multiple goals and the agent might be pursuing multiple goals at the same time. Here in the GOLAC, we are only pursuing one goal at the time. Many goal reasoning architectures are trying to learn new goals. In this GOLAC architecture, the number of goals is fixed. If we were to add new goals, then we will need to do something. And we have been in conversations with David and I forgot the name from my other colleague. I'm sorry, but there's somebody else who has an idea of how to do this. And then the other part that we look at is we look at the kinds of state sequences that are generated, and using formal grammars, we model what those systems do, and we're able to explain why FONS is able to solve some problems that HDQN cannot using analysis of these grammars. And with that, thank you very much. And I appreciate if somebody read the questions, because since I'm sharing my screen, I probably will have to open here. So thank you.
Thank you. Any questions? Anybody? Let me ask you, Hector, what is the knowledge underlying the options mechanism? What do you need to know in order to make the selection there? And also the goal selection in the first place.
Okay, so let me go back here about that. Let me just go to the architect directly here. Yes. Actually, no. Let me show you the actual architecture inside. I have a backup slide. Probably that would be better to ground. Yeah, this one. So what the output of the goal selector is a vector, and there is one entry in this vector for each goal. So in this simple corridor domain, there were 6 possible goals, which is 6 locations where the agent can go to. So that's the output. The input will really depend on what we're doing. So one of the domains that we try is this Doom game, and in the Doom game, we're giving snapshots. So for that one, we have to do a convolutional network to reduce the dimensions and flatten basically the structure. We use, this is the memory mechanism that we are using, and from that we select which goal to choose. So it's intrinsic in the mechanism. This is of course a multi-level deep learning network. It's simply the mechanism that will give basically for each of these goals a possible value, and we select the goal with the highest value after learning. Before learning, we select, we do the usual epsilon greedy, where we select the goal with the highest value most of the time, and from time to time we do a random goal.
Is there a way for you or the system, no, the system probably not, but for you to understand whether the goal selected, why a particular goal was selected?
The short answer is no. That's the big problem with deep learning or open question. I'm trying to say problem. That's a big open question, right? So you have these multiple networks, and then we need to know. We would like to explain why selecting this goal over this other goal. And the answer is, well, everything is distributed in the weights. That's a big research topic. So the whole movement of explainable AI is trying to do that, and this will be an instance of that.
Very good. Any more questions, please?
I have a quick question. This is Dustin. Hector, did you by any chance come across some work called Universal Value Function Approximators? I know this might be a little out there.
Universal Function Value Approximators. I could speculate what it is, but I'm hesitant since I'm being recorded. So
I'll follow up with you.
Come across it, but the name sounds very descriptive.
So they had some work where they basically were able to learn. It's a deep learning system where they're able to have goals, like kind of a variety of goals that an agent could learn to achieve. But it seemed very restrictive in the types of goals. And so I just wondered, as maybe a next step of this work, this is super interesting. I wonder if the different types of goals and what these systems are capable of for those.
Right. So something we're looking at is, David, are you there? I forgot the name of the person who suggested the case-based reasoning. I'm blocking on his name.
Yeah, I'm not sure right now, Hector. I have to think about it.
The person who suggested combining this with case-based reasoning.
Is it possible you're thinking about Andrew McCallum?
No, never mind. As somebody who worked with Kalian. Okay. Dustin, we have been started looking into a possibility of being able to learn new goals and extend this architecture to be able to learn new goals that are not in this output vector. And we're looking at possible case-based reasoning techniques. One colleague of David and I suggested an idea, and we're probably going to pursue that. I'm blocking on the name, but yeah, that's what we're looking at.
Yeah, you should take this offline for this particular one because we need to go on, please.
Okay,
Thank you, Hector.
Thank you, Hector.